Welcome back to physics, only half of my class. Anyways, so today, I think we got to make a decision. So basically, we got a few more things to do, which is finish up, first of all, self-inductance. And then after that, we're going to throw those into circuits and see what they actually do with circuits. But that would take up the entire time, and I don't really want to do that yet. So I think what we're going to do is just talk about inductance, do an example of inductance, and then we'll do a review, and then I'll bring up some group assignments, and then that'll be stuff. So we'll put these guys in circuits after the exam. So we'll talk about what happens when these guys are actually put into circuits. So great. So good. So let's remind ourselves that again, what we talked about yesterday was two different types of inductance. So we had again mutual inductance and we had self-inductance. Okay, mutual inductance is when the circuits are feeding off of each other. And then we have the self-inductance when it is feeding off of itself. So again, we're only going to look at the self-inductance in this case. So yeah, so let's say here is my solenoid. So here's my solenoid, my inductor. And again, I'm going to have current running in. I have my loops. But let's say the current is increasing because I just closed the switch. So it goes from zero currents trying to go to some sort of maximum currents. So that means that my current here is increasing. So if I follow the directions of the loops, what I know is at this point up here, my current is coming out, which means my magnetic field is going to curl around in this direction, which means my magnetic field then is going to point along the axis of the solenoid, which we already do. But anyways, as it's pointing along the axis of the solenoid, that means that this magnetic field then is increasing. But since magnetic field is increasing, that means the flux is increasing, which means that it wants to generate its own magnetic field in the opposite direction, which is this one, the induced magnetic field, which is going to drive the current backwards in the opposite direction, which is what we call the back current. Now, what that does then is it causes a lag in the current, so the current doesn't go all the way from zero to maximum instantaneously. It takes time to actually build up due to this back current trying to flow back in the opposite direction. But since I have a back current also trying to flow in the opposite direction, what that also creates then is the potential difference between these 2 points. So in this case, the potential difference between B and A is not going to be equal to 0 like it would be in a regular wire. There's going to be some sort of potential problem. So this potential difference is what we call the back EMF. So in this case, the back EMF then is equal to the change of potential going from B to A. So that's what we call the back EMF. So in this case, we want to know what is the back EMF, and then from there, also, how do we define what the inductance of this object is? So what we're going to do that is we're going to say, well, the flux through each one of these loops will be identically the same, but I have n number of loops. So that says that I have an n number of loops times the magnetic flux through each one of these loops. And what I know is that this has to be directly proportional to the current, which is actually flowing through the system, because the magnetic flux is dependent on the current. Great. Now, the constant proportionality is what we're going to call L, which is what's known as the inductance of the inductor. Called the inductance of the inductor. So in this case, our solenoid is what's known as an inductor, and L then is the inductance of that inductor. So all this thing says then is the number of loops times magnetic flux through each one of the loops is then equal to the inductance times the current, which means that our self-inductance then is defined then as the number of loops times the magnetic flux divided by the current. So this is the definition then of self-inductance. Now, from this, we can also then get what's the back EMF. So remember that Faraday's law says that the EMF is then equal to negative the number of loops times the time rate of change of the magnetic flux. But from this, we know then that the number of loops times the magnetic flux is then equal to the inductance times the current, which means the number of loops times the time rate of change of magnetic flux, according to this, then is going to be equal to the derivative of the right-hand side. But the inductance of the inductor is a constant, which means the only thing that's changing on the right-hand side here is simply the current. So this is then going to be equal to the inductance times the time rate of change of the current, which now I can use all this here and put it back into the right-hand side, throw in a negative sign. What this finally then says that the back EMF, or the potential difference between A and B, is then equal to negative the inductance times the time rate of change of the current. So this is what we call the back EMF. So the back EMF inside of this inductor then simply equal to the inductance times the time rate of change of the current, which means that what? As long as my current is changing with time, I then have a back EMF. But as soon as the current stops changing with time, meaning when it does reach that maximum amount of current, This term is going to go to 0, which means the back EMF is going to go to 0, which means it's just going to flow through there as if it was a straight line. So basically what happens then is, as I'm trying to charge the inductor, going from 0 current all the way up to maximum current, again, I'm going to get this back EMF because I have the back current trying to drive in the opposite direction. Well, once this current here fully overcomes this current, so this overall stops changing, in this case, I'm going to have a constant magnetic field with a constant magnetic flux, which means in this case, I'm going to have 0 back current, I'm going to have 0 back EMF. So this EMF is going to go away once this thing reaches the maximum amount of current, in which case the inductor acts just like a straight line. Okay with us? Now, what's the point of putting in an inductor? Well, I alluded to this before, where I said that an inductor or a solenoid is the magnetic analog of a parallel plate capacitor. So the point of putting an inductor into an electrical circuit is to actually store energy by the amount of work it takes to overcome the back EMF or the back current. So as I'm trying to drive current through the system, the back current is going in the opposite direction, which means my battery has to do work to overcome that back current, which means I'm going to store energy just like I would store from a parallel plate capacitor by having the battery do work to, in this case, get it from 0 amount of current up to a maximum amount of current, or before it was go from 0 amount of charge up to a maximum amount of charge. So this thing has exactly the same purpose as a parallel plate capacitor or any capacitor, and the fact that it's put in there to store energy for later use. That's the point of an inductor. So, okay, so now we want to know then is, what energy is stored? So what energy stored within the inductor? Now in this case, the energy is going to be stored, unlike the capacitor, which was stored in the charge. In this case, it's going to be stored inside of the current. So let's think about this. So what we know then is that what? We want to know what is the work, right? Because we know the work then is going to be equal to the energy which is stored. So by conservation of energy. So the amount of work that the battery does in this case is then equal to the energy which is going to be stored. Right, that the battery. How much work is the battery doing? Well, what do we know? So we know energy, so we know power is equal to the time rate of change of the energy. So in this case, then what we can say is, well, the differential amount of work then is then going to be equal then to the power which is delivered by the battery times then the differential amount of time it takes for this thing to actually occur. Which means that if I integrate then both sides, then the work which is supplied by the battery then is then going to be equal to the integral of the power which is being supplied by the battery integrated over time. What was the power being supplied by the battery? Well, we know from chapter 27 that power for any electrical element is simply equal to the current times then the potential. Now, in this case, what I care about then is not necessarily the potential of the battery, but the potential at which it has to overcome, which is the potential which is the back EMF. So in this case, what I really care about is that this is then going to be equal to the current times then the back EMF. In this case, the magnitude of the back EMF. So what? Let's put all this stuff together. So this is then going to be equal to then the integral of the back EMF, which we now know is equal to the inductance times the time rate of change of the current, times the time rate of change. So in this case, I want to integrate this over the time. Well, what happens to this dt here and this dt here? They're going to cancel each other. Good. So this term is going to cancel this term. So this then is going to be equal to, let me move to a new slide, that the work done by the battery, which is then equal to the energy which is being stored, is then equal to the integral of the inductance times di, integrated then from 0 to I. Oops, I forgot an I here. I forgot this I here. So there should be an I here. Sorry about that. I times L times E. There we go. Sorry, forgot to put my I there. Now again, inductance turns out is simply a constant, so that guy's going to pull outside of the integral. So in this case, we can write this then as the inductance integral from 0 to the current of the currents integrated over the currents. Well, what's the integral of the current integrated over the current? So it's IDI. got I squared over 2, so this is then going to become 1/2 inductance times the current squared. So this is the total amount of energy which is stored within inside of the inductor. This is the total energy. So the energy stored then within inside of the inductor is then equal to 1/2 the inductance times then the current running through the inductor squared. So this is my energy which is being stored. Okay. Now from here, we can do the same thing that we did before, which means we can define now what's known as the energy density. So this is going to be our magnetic energy density. Which remember is the same thing then as the energy being stored per unit volume. So from here, if I pull some shenanigans, what I can basically find is that this is equal to 1/2 the magnetic field squared divided by mu naught. I'm not going to bother deriving now. We'll see where that actually comes from later. So just to contrast with parallel plate capacitors, so remember for capacitors, what we had was that the energy stored was equal to 1/2 the capacitance times the charge squared. No, this is CV squared. Okay. We also had that the electric energy density was equal to 1/2 epsilon naught times the electric field squared. So these guys have exactly the same structure as they do for the parallel plate capacitors. Now, let's make another note about self-inductance. So it turns out self-inductance here, just like parallel plate capacitors, this thing is actually only dependent on geometry. It only depends on geometry. So again, just like parallel plate capacitors, which only depended on geometry, it turns out self-inductance also only depends on geometry, which means that if I change the geometry, I then change the inductance on the inductor. But if I don't change the geometry and I only change the amount of current, or if I change the amount of magnetic field, I don't change the inductance. I just change the response of the other object. So if I change the current, then I change the size of the magnetic field, but they change proportionately so that the inductance stays exactly the same. So the inductance of an inductor only depends on the geometry of the inductor. It does not depend on the currents or the magnetic flux. Those two are directly related to each other. But again, the whole entire point of a inductor is simply to store energy. It stores energy. What this one says is that the energy is actually stored within inside of the currents, which is running through the inductor. In this form, what this says then is the energy per unit volume is actually stored within inside of the magnetic field itself, just like with the parallel plate capacitors, which says that the energy stored per unit volume is actually stored within inside of the electric field itself. So just interpretations of the same thing. But okay?
So when we talk about volume,
Yes.
so if we're storing the energy in a solenoid, we're talking about the volume of the magnetic field, which is only inside of
Correct.
the loops.
That's right. So it's only inside of the solenoid itself.
Okay.
Exactly. So in this case, if I was looking at a front view of the solenoid, exactly. So my magnetic field is pushing out in this direction. What we're saying then is if I cut a small volume here inside of the solenoid, then that's the amount of energy per unit volume stored here. That's right. So this is what little b or little ub is representing. But you're absolutely right. So if I go to the outside and I cut a small section out here, then there's no energy density here because there's no magnetic field. Exactly. So on the inside, it's just equal to 1/2 e squared divided by mu naught. But on the outside, it's equal to 0 because there's no magnetic field. Exactly. Right. So it's just the energy per unit volume when inside of the solenoid, as opposed to on the outside. Okay? Quick dash of inductors. But again, it's the same idea as capacitors. So again, the point of a capacitor is to store energy for later use. The point of a solenoid is also to store energy for later use. The difference is one is electrical, where it's storing charge, so it's storing electric field. The other one is magnetic, it's storing current, so it's storing magnetic field. But they do the same function. That's the point of them. So let's do an example. Let's see how we actually calculate a inductance, or in this case, a self-inductance. So typically, we're just going to call self-inductance inductance, because that's what we usually call it. Well, what this says is determine the inductance per unit length of a coaxial cable whose inner conductor has radius of R1 and outer conductor has radius of R2. Assume the conductors are thin hollow tubes, so there's no magnetic field within the inner conductor and no magnetic field outside of the two of them. So the only magnetic field is between the two conductors. And it says the conductors carry equal and opposite currents. So it's a coaxial cable like we know before. Okay, so here's my example. So what's going on here? So we draw kind of a side view. So here I have my internal one. And outside of this, I have my external. So we're told that this one has a radius of that little R1. This one had a radius of R2. So this is my radius of this guy. Okay. Then this guy has what? Some shape to it. So it's doing something like this. And we're told is that these guys have currents of equal magnitude. So this one say has current running in this direction. The inside one has current running in this direction. So in that case, we know by Ampere's law, the magnetic field running outside is simply equal to 0. But we're also told that this guy is actually a hollow tube, which means all the current is only running along the surface of the tube. Now, is that important in this example? The answer is actually no. It doesn't matter if it was running throughout the entire thing or only on the surface. It doesn't change the result. But again, that's just what it wants us to look at. So all that means is since it's all running along the outside of my pen here, means in the middle I have actually no current running through, so there's no technical magnetic field on the inside, but I'm going to have magnetic field between the two cylinders. So I'm going to have magnetic field in this region only. In this case, all my magnetic field is going to contain in this region here. So my B is not equal to 0. So what we want to know then is what is the inductance per unit length? So how are we going to calculate this? Well, we now know that what the number of loops times the magnetic flux is equal to the inductance times the current, which again means that the inductance then is equal to the number of loops times the magnetic flux, all divided by the current. So the first thing we're going to have to do then is calculate what is the magnetic flux in the region where I have a non-zero magnetic field, which means in between these two conductors. So that's the first thing we're going to have to do. So let's look at that first. So first things first is what we know is that what outside of a cylinder, the magnetic field looks like that of a straight line. Is what we found using Ampere's law, which means that here we put our thumb in the direction of current, our fingers will turn around in the direction of the magnetic field, which means in this case it's going to circle around in this direction, which means down here it's going to be coming out, up here it's going to be going in. Okay, so let's go ahead and draw that. So here I know my magnetic field is going to be doing this on the interior. Where up here, what that means is it's going into the board. And then down here, it's coming out of the board. Now, we also know, again, by Ampere's law, that the magnetic field on the inside here, gray, I guess, has a magnitude, which is equal to mu naught times the current divided by 2 pi r. Okay, so this comes from Ampere's law. This is something that we did last chapter. Now, in this case, what we know then is that what? Our magnetic field is actually spatially dependent, which means if I start here at this radius and I integrate out to this radius here, what's changing is the radial direction, which means that in this case, the magnetic field is not constant as far as the area is concerned. It's changing. Because my area is changing in this direction, which is the radial direction, my magnetic field is also changing in that direction, which means I am going to have to do an integral in this case. So let's write that down. So in this case, let's look at the magnetic flux. So our magnetic flux then is going to be equal to the integral of B dot dA, where again we know B, at least magnitude, is equal to mu naught I divided by 2 pi r. Good. So the question is then, well, what is dA? So how are we going to determine dA? So dA then is going to be some differential area which is inside of this section here or this section here, but technically around the entire thing. Well, let's just look at either the top section or the bottom section. Which section you want to do? Top section or bottom section? Taryn, what section? Top, good. So in this case, what I have to do then is I'm going to take this thing and I'm going to chop it up into a small dA. So here's going to be my dA. So what I'm going to do is I'm going to chop this thing into a dA where the direction of my dA points in exactly the same direction as the magnetic field. Okay? So basically, since my magnetic field is pointing inward, I'm drawing a dA here, so this has an area vector associated with it. I'm going to take that in the same direction as the external magnetic field. So for this thing, what that means then is my dA is also going to be pointing into the board. Now for this, I'm going to cut it into some length. So this is going to have a length of L, but it's going to have a thickness to it. And that thickness is going to be this thickness here, or that thickness, I'm going to call it dr. So what I'm doing is basically imagine I'm cutting out a small slice across here, right? So this is my distance between these two plates. I'm going to cut a small slice here where the thickness of that slice is in the radial direction. So that's why it's dr. But it has a length to it of simply L because the magnetic field doesn't change in the horizontal direction. It's only changing in the vertical direction, radial direction. So basically, it just doesn't matter how long I cut this thing to because the magnetic field doesn't change going this way. It only changes going this way. Okay, so what this means then is, what I know now is that dA then is going to be equal to that length times the thickness at which I cut it, which is like d. Now again, in this case, I'm choosing dA to be in the same direction as the magnetic field, which means the dot product here simply becomes multiplication. So this is now going to become the integral of B, which is mu naught I divided by 2 pi r times L times d. That's my dA portion. Okay. Now here, mu naught I, L, 2 pi are all constants. I'm going to pull those outside of my integral. So it's going to become mu naught I times L divided by 2 pi integral dr divided by r. And I'm going to integrate that from where? I'm going to integrate it from this position here to this position here, which means I'm going to integrate it from the inner radius to the outer radius. I'm just simply going to integrate this guy then from R1 to R2. What's the integral of dr over r? Natural log, good. So this is now going to become mu naught I times L divided by 2 pi natural log of then R2 divided by R1. Okay? Now go back to here. What this then says is that L is going to be equal to the number of loops times that magnetic flux divided by the current. Now in our case, how many loops do I have here? 1. So N is just going to be 1. So all I'm going to do then is take this magnetic flux and divide by the current. So here we know that is N is simply equal to 1 since there's 1 loop. Which means that my inductance then is just going to be my magnetic flux divided by the current. So if I plug in my result, this is then going to be mu naught times the current times L divided by 2 pi times then the natural log of R2 divided by R1 divided by the current. So that current shows up here, so that's going to cancel this current. So it actually doesn't depend on the current, which then just gives me mu naught L divided by 2 pi times the natural log of R2 divided by R1. Now in our case, what we want though is the inductance per unit length, which means all I'm going to do is divide both sides by the length. So finally, my answer is that the inductance per unit length then is equal to mu naught divided by 2 pi natural log R2 divided by R1. This is my self-inductance. Now again, just quickly kind of go over, again, we said that the inductance only depends on geometry. It doesn't depend then on the current or the magnetic field, which we can actually see from here. So again, here, these are just geometrical terms, R1 and R2. It doesn't depend anything then on the current or on the magnetic field. This guy is simply a constant that depends purely on geometry. Okay? What's up, Omar?
How do we get the areas out here?
Oh, so in this case, so again, we have to take into account that our magnetic field here is what, changing going from this location to this location. So here I'm just choosing to cut out this section here, but again, since my magnetic field doesn't change going from this point to this point, it's independent of the length at which I choose. So if I wanted to, I could cut this all the way down to this side and just call that completely L. Doesn't really matter. But what does matter is that since the change is going vertically away from it, then I have to make sure that I choose a small differential section at which I'm going to integrate over.
You
So-
wouldn't do like circles or
Well, yeah, so, well, in this case, again, I want to mimic what the magnetic field is doing. So technically, you are correct. What I'm really doing is I'm cutting out a cylindrical shell that actually goes around the entire outside. But I'm just drawing this small thing like this just to illustrate a little bit better what we're actually doing. But when I'm trying to draw a cylindrical shell going around, it's kind of
how like. I would have done something like 2 pi now.
Oh, you mean
Yeah.
for the circumference and everything?
Yeah.
Well, again, all I care about is the flux through some portion of it, and then I extract it over the entire thing. So, yeah, so I think you get the same result, regardless of how you did that. But, yeah. Everyone okay? Now, at this stage, the plan was to now put these guys into circuits and see what actually happens, but we only got, what, like 20 minutes left. So instead, we'll do a review for Friday's or Monday's exam. Today is Friday. So let's do a review instead. And then we'll put these guys in circuits after the exam. So come back on Wednesday, we'll do it then. So let's do our review. Talk about what we should expect. And I actually have 3 more group assignments for you. So that's going to give us, what, 9 group assignments? All right. So hopefully we get that part. So our first one is, we only have 2 chapters in this case. So we have chapter 29. Good. So what are we doing in chapter 29? So first thing we said was that we know that if we have a wire in an external magnetic field, this guy's going to feel a force, where the force on that wire then is going to be equal to the current times the differential length crossed then by the magnetic field. Again, this is our general expression. But this thing also reduces then to the current times the length times the magnetic field, as long as this thing is straight and B is equal to a constant. So as long as it's straight and B is equal to a constant, I have the second definition. But if it's not straight, or if the magnetic field is not constant, or both, then I would have to actually integrate and use the first one. Good. We also found that the force on a charged carrier moving in an external magnetic field is simply then given by QV cross B. So this is the force on a single charged particle. As long as the velocity is what? Perpendicular to the magnetic field. So if B is perpendicular to B, this thing then is going to move in a circle where I'm going to have what? MB divided by R is equal to Q times B. From there, I can get the radius, I can get the velocity, I can get whatever it is that I want from this expression. So this is true. This. Along with this, we also then have that the period is equal to 2 pi times the mass divided by the charge times the magnetic field, which is also equal to 1 over the frequency, which is what we call the cyclotron frequency. So all this here is true amongst themselves. Okay. From here, we looked at the Hall effect. Good. So the Hall effect basically says that the Hall EMF is then equal to the velocity times the width times the external magnetic field. So in this case, if this is my object here, my magnetic field, say, is pointing in this direction perpendicular, and I have currents running through across here in this direction, and my Hall EMF is this across here. So this is my Hall EMF, where this distance here then would be the width. So that's my Hall effect. We also looked at the Lorentz force. So Lorentz force. So Lorentz force says that the total force on a charged particle in both an electric field and a magnetic field, total force, is then equal to the charge times the electric field plus the velocity crossed by the external magnetic field. So this is what we call the Lorentz force. Okay. From there, the most interesting thing about that was velocity selectors. So a velocity selector, what we said was that we have parallel plate capacitors, which had an electric field pointing in one direction, a magnetic field crossed in the other direction. In this case, we can tune it so that the velocity, which is allowed to go through of a particle unmolested, will then be equal to the ratio of the electric field to the magnetic field. So that would be this charged particle here moving through with a constant velocity. Those are velocity selector. After this, we looked at loops of wire and external magnetic fields. So we saw from here is that this guy has a torque, or the torque in this case then is equal to the magnetic moment crossed by the external magnetic field, where the magnetic moment is equal to the number of loops times the current times the area written as a vector, which also has an energy associated with it, which is equal to the negative of the moments dotted then by the external magnetic. So that's this guy. Don't worry, I'll write down all the right-hand rules at the end. So. That's pretty much it for all that. And then after that, we started to look at how do we actually calculate magnetic fields. So we looked at Biot-Savart's law. The Biot-Savart's law says that the magnetic field at some point P is then equal to mu naught times the current divided by 4 pi integral, we have enough room in here, dl crossed by r hat all divided by r squared. So this is Biot-Savart's law. For this guy, we then looked at Ampere's law. So Ampere's law says that the closed loop integral of the magnetic field dotted by the differential length must then be equal to mu naught times the current, which is being enclosed. Last thing we looked at was then the force between parallel wires. Force between parallel wires, what we found was that the force on 1 by 2 was then equal to the force on 2 by 1 magnitude, which is then equal to mu naught times the current I1 times the current I2 times the length, all divided by 2 pi d, where again d is the center to center distance between the two wires. So this is my distance. From here, what we found was that if the currents are in the same direction, that's an attractive force. But if the currents were in the opposite direction, that then manifests itself as a repulsive force. And that's it for chapter 29. That was basically everything we did. What's up?
Do we go back to Lorentz force?
Oh, Lorentz force? Yes. So that's basically it. We spent a lot of time on all this stuff, but I was mostly just kind of doing examples, describing all these things, making sure we're all comfortable.
Is that an E plus B or E plus B?
This one is an E plus B cross B. Yeah. Sometimes we write too fast, your pluses look like crosses, crosses look like pluses. And it's all. So it's okay. So from here, we then moved on to chapter 30. So let's talk about chapter 30. That blue, chapter 30. So chapter 30 was our big Faraday's law. So in this case, what we found was that Faraday's law says that the induced EMF is then equal to negative the number of turns times the time rate of change of the magnetic flux, where the magnetic flux is then equal to the integral of the magnetic field dotted by the differential area. So this was our baby version of Faraday's law. And then our actual version of Faraday's law says that the closed loop integral of the electric field dotted by the differential length is then equal to negative the number of loops times the time rate of change of the magnetic flux, which then is the integral of E dot dx. So this is our full version of Ampere's law. Not Ampere's law, sorry, Faraday's law. Things to note from here is for what we call motional EMF. I'll write that over here. Motional EMF. We found in this case is if I had a rod moving in an external magnetic field with some velocity v, say my magnetic field is pointing into the board. In this case, we found was that the EMF generated was equal to the magnetic field times the length times the velocity, where the length is simply how long this rod is. So this is the length. So this is what we call motional EMF. After this, we basically then just started looking at what? Inductors, right? So from our inductors, we then found that our self-inductance is then equal to the number of loops times the magnetic flux divided by the current, and then at the back EMF we talked about today is equal to negative of the inductance times the time rate of change of the current, and then the energy stored is then equal to 1/2 the inductance times the current squared. So this is all stuff for inductors. And that's it. That's all we did in chapter 30. What's up?
For the back EMF, what
Yes,
scenarios would you actually have to take in to find the current?
that's a great question. And that would what we would have seen if we actually did circuits.
Okay.
So we won't see that technically until after. So as far as an integral over this guy is concerned, you wouldn't have to worry about that yet. But again, we'll see that when we get back. So after the exam, we're going to look at two different types of circuits. We're going to look at an LC circuit, which is a capacitor connected to an inductor with no battery sources. So in this case, you have simply, you charge up the capacitor and put it in. I'll get to the punchline now. Basically, it acts like a harmonic oscillator. So we'll see that later. And then the other one is a LR circuit, which is an inductor connected to a resistor, connected to a battery, or not connected to a battery. And then that acts just like an RC circuit, where the current basically goes to 0 over time. So it exponentially decays. But so in that case, you would then have to do the integral over the current to find the actual current as a function of time. So that's an example. We would have to actually do that. But again, we won't see that until after this exam. So we'll do those real quick. But yeah, so that's about it. So that's all we did in chapter 30. What's
Is
up?
that an exponent on your stored energy, or is that just
It's just stored. Yeah. So this part.
or like no behind the eye?
Oh,
Is
that's
that
a
an
square.
LI?
That's a square.
Okay.
Doesn't look like a square. How's that? A little bit better. Okay. Okay. So that's about it. So let's talk about what we should expect. So first thing is, let's go back. So first things first is definitely a long problem will be Ampere's law, just like we did Gauss's law. So look at some examples of Ampere's law, but this is definitely going to be a long problem. So in this case, again, coaxial cable, something like that. You know, so find a magnetic field at different regions based off of current densities and all that kind of good stuff. So other things to note on this one is remember how current relates to current density, and that's in general that the current enclosed then is the integral of the current density integrated over the area, just in case it is non-constant. Good, so that's that. Other long ones to think about are, so basically your other long ones are going to be most of this page actually. So probably everything through here, I would say, long problem. So what do I mean by that? So what I mean is it's either going to be force on a wire or force on a charged particle. But if it's a force on a charged particle, then you have all this stuff to worry about, as well as the Lorentz forces, which means, and part of that problem would be also velocity selectors. So let's call this long problem number 1. So this would be part of long problem number 2 if it had to deal with the force on a charged particle. But again, if it's a force on a wire, in that case, then this would be important, as well as this. Also be part of long problem number 2 if it was a force on a wire, because in this case, I'm going to have force between parallel wires and things like that. So a little ambiguous, but that's but yeah, odds are it's going to be more of the force on a charged particle, not the force on a wire. What's that? So that gives us 2, and then the last long problem. Long problem number. Faraday's law. In this case, I would expect more motional EMF type stuff as opposed to the second definition. So as opposed to this guy, I would be looking more at this portion. So the motional EMF type stuff. So looking at induced EMFs. Now from here, of course, since you're looking at induced EMFs, the important things to look at are things like the relationship between current and potential, which means Ohm's law would be very important to this. So remember that potential is equal to current times resistance, Ohm's law. Power loss, remember power loss is either equal to I squared over times R or V squared over R, one of those two. But things like power loss, also power delivered. So technical definition of power, which is then force dotted by velocity, things like this. So pay attention to those things. All this would be important. So a lot of earlier things that we did before. So chapter 27 type stuff. Ohm's law, power loss through a resistor, as well as all the different right-hand rules, all that stuff. So force on a straight wire, et cetera, et cetera, et cetera. So emotional EMF type stuff. So that's going to be all your long problems. So typically emotional EMF type stuff, forces on a charged particle or on a wire, or again, Ampere's law. So these are going to be my 3. Short problems. So let me do short problems in green. This one is definitely going to be a short answer one. So short answer. So torque on a loop of wire. That's definitely going to be a short one. What else? Hall effect would also be a short one. Also be a short answer one. For Hall effect, also look at the example that we did in class as well as group assignment, which dealt with things like current density as well as little n, which is the number of charged particles per unit volume, drift velocity, things like that. So also things from chapter 27 that we brought into that problem as well. So look at things like that for that particular problem. Then if this portion here doesn't show up as a long problem, I would expect that this would also show up. Sorry, not that portion. So the force on a long wire. So this would also be a short answer one. If it doesn't show up elsewhere, which means this would also be part of the short one. So if it doesn't show up in a long problem, it will definitely show up as a short answer. Which then brings us to Beal-Savard's law. So Beal-Savard's law is interesting, but we've already done most of the interesting cases for it, which means, so sorry, but it's fine. So if we're only looking at basically wires, we can only do so much interesting things with wires. So great. That then brings us to inductors. So inductors then would be what I haven't mentioned yet. So this would be then extra. That's about it. So the last thing we'll talk about then real quick is our right-hand rules. Let's go through all of our right-hand rules. So we have right-hand rule number 1. So again, this is for a B field about a straight wire. Or any wire, I should say. So B about a wire. So again, right-hand rule number 1 says that number 1, thumb goes in the direction of current. And then number 2, fingers curl in the direction of the magnetic field. So that's right-hand rule number 1. Right-hand rule number 2 deals with anything that is a cross product. So this is anything that's a cross product. So things that are cross products are, again, force on a wire, the force on a charged particle, the torque on a current loop, anything like this, that's a cross product. So here, what we have are 3 vectors. We're to get vector A crossed by vector B is then equal to vector C. So in this case, step number 1 is point fingers in direction of A. Step number 2, curl towards B. So curl towards fingers towards B. Again, in the direction of smallest angle. Best way to think about that is your palm has to be pointing in the direction of B. So always have your palm point towards B. And then number 3, thumb, which is always perpendicular to the hand, points in direction of C. So this is right hand rule number 2. Steps. Right hand rule number 3. This has to do with magnetic moments and areas. So here, step number 1, curl fingers in the direction of I around the loop. Step number 2, thumb. Again, it's perpendicular to the hand. Points in the direction of mu, which is the same direction as A. And then we have, finally, modified version of right hand rule number 3. This is technically for Faraday's law. So for this one, step number 1 is we put our thumb perpendicular to hand in direction of being induced. Step number 2, fingers curl in direction of I induced. So this is right hand rule number 3, modified version. So it's the same thing as this one, it's just opposite. So again, here our thumb's giving the direction of this after we curl, but since this is in the same direction as the magnetic field, it's the same thing, it's just done in the opposite. So that's it. Those are our 3 for right hand rules. So these will all, of course, be necessary because anytime you deal with magnetism, you always have to use the right hand, which this exam then is always great for me because I get to watch you do this and I get to laugh at you when it's great. So having said that, we got a couple minutes here. So let me talk about real quick the last 3 group assignments here for funsies. We're gonna have time to work on, but that's fine. So I have 3 of them here. So the first one says we have a conducting rod of mass 0.75 kilograms and resistance of 1 ohm is pulled in the horizontal direction across 2 frictionless parallel rails at a distance of 12 centimeters apart by a massless string, which passes over a frictionless pulley and is connected to a block of 7 kilogram mass. And it's happening in an external magnetic field, which is oriented vertically at a constant of 1 Tesla. So then says the bar is released from rest. What is the terminal speed? So what's going to happen is, so let's draw a picture here. So let's draw this. This is our number 1. So let's draw it from a side view first. So from the side view, here's my conducting rails. Here is my block, which is sitting on top. This thing has a mass of M. Connected then over by a string over a pulley, which is connected to another larger mass down here. Let's call that guy capital. Good. From a top view, that means this here's my 2 conducting rails. Here is my mass. Again, this thing's being pulled in this direction by that string. So what's going to happen is what? Initially, since there's no, this way. Also, we know there's a vertical magnetic field. So here's my vertical magnetic field. In this case, it's pointing out in this direction. Good. So initially, since there's no velocity, this thing is released from rest. That means there's no current running through the system yet, which means there's also no force acting on this guy. Now, this thing is going to cause then a acceleration of this due to this pulling straight down, causing this guy to start accelerating in this direction. But as it accelerates, its velocity is then going to get bigger. But as the velocity gets bigger, then the amount of magnetic force that this thing is going to feeling in the opposite direction is going to get bigger and bigger and bigger and bigger, which means that you're going to end up with a time-dependent velocity. So this thing's going to start off with a maximum velocity, and that velocity then is going to decrease over time until eventually what happens is the magnetic force is going to equal the tension pulling in the opposite direction, at which point in time you're going to reach terminal velocity. So in this case, what you want to find out then is what is your terminal velocity? So how fast is this thing going to be moving in this direction maximum? So you want to know what is the terminal velocity of this thing. And again, just to remember, terminal velocity occurs when the acceleration is equal to 0. Which means in this case that you're going to have a tension force pulling in this direction. You're going to have a magnetic force pulling back in this direction. So the two forces have to be equal and opposite from each other. So that's the first part. Let's look at the second one. So the second one says we have an 8x8 square loop. It's halfway into a magnetic field perpendicular to the plane of the loop. It says the loop's mass is 10 grams and has a resistance of 0.01 ohms. A switch is closed at t is equal to 0, causing the magnetic field to increase from 0 up to 1 Tesla in a time frame of 0.01 seconds. So from this, you want to find out what is the induced current inside of the loop. And then basically what's going to happen is that induced current is going to create a force onto the wire, which is going to cause that wire to try to kick out of the magnetic field. This is effectively a railgun. Okay. So what you want to know then is what speed is this guy actually kicked out? So let's draw a picture for this one. So we know what this guy looks like. So what's happening here is here's my square loop. My square loop, L. This thing is sitting in a magnetic field, but only half of it is sitting inside the magnetic field. So this is going to be my magnetic field. For funsies, let's say it's going out. On this side, the magnetic field is equal to 0. Good. So my effective area is simply this area here. So what's going to happen is, again, we're going to increase the current from here, causing the magnetic field to increase from B is equal to 0 to B is equal to 1 Tesla in a time frame delta T of 0.01 seconds. So what it's going to do is it's going to force a current to move throughout this loop here, which causes a force. In this case, I'll let you prove this to yourself. It causes the force to then point in this direction, causing the magnetic force to then try to kick this thing out of the magnetic field. So what I know in this case then is, again, what is the velocity that this thing has while it is moving out of the magnetic field? Okay. One more to talk about, and then I'll let you go. So this says, what is the induced EMF generated by a rigid rod of length L rotating perpendicular to an external magnetic field with a constant angular velocity? So let's draw that picture too. So the third one, what I have is, let's say my magnetic field again pointing out. Here is my rod. This rod has a length of L to it, has a fixed point. So let's say this is my pivot point. And this thing is going to rotate around, say, in this direction with a constant angular velocity of omega. So what I want to know then is, what is the EMF generated across this thing? So what is my induced EMF? Now, in this case, I'll tell you, you have to do an integral. Okay, so for this one, you'll have to integrate to determine the EMF. And the reason for that is, as this thing is rotating, even though it has a constant angular velocity, what's true about the velocity here versus the velocity here? They're different. Exactly. So the further it goes away, the faster it has to rotate, which means the faster it has to go, which means the more EMF that's going to be generated. Okay. So basically, at one side, I'm not going to have a lot of EMF, but on the other side, I'm going to create a huge amount of EMF due to its actual movement. So what you'll have to do in this case then is, again, start off with the differential amount of EMF, then is going to be equal to the velocity times the length of this object. Simply, I'll leave it as L in this case. Times then the speed. Okay, so the length in this case is only referring to, say, this portion here. This is the distance F. But the speed we know is related to the angular velocity by this amount. So you have to basically put all these pieces together and then think about that. So one of these is going to be a DL, basically. So in this case, since I'm looking at the differential amount in here, actually this L here is going to be a differential length here. So this is going to be actually B times DL, where this is DL, which is this differential length across here. This is happening at this length of L here. So effectively, this is going to become what? B times omega times L times DL, and then finally just integrate both sides. And then that'll give you the total amount of EMF, which is different. So that's it. I went a little over. So have a good weekend. I'll see everybody on Monday for fun for you, not for me. How would I grade it? You too, Dan. See ya.